Here I'm going to make a few videos about intermolecular forces. Even though this channel is organic chemistry, we need some basic concepts from general chemistry, and I have found that still students need a review on that. So that's what I'm doing in this video. So first, these are forces between molecules, so intermolecular forces. Now, but to understand those forces, there are a couple of things that we need to take into account. One is we need to be able to determine if we have polar bonds. And for that, I need to see where my atoms that are bonded are in the periodic table and determine if we have differences in electronegativity. That's one factor that we need to take into account. The next one is the molecular geometry. And we're going to see examples of that because some molecules may have polar bonds, but overall may not be polar. Then we're going to be talking about the types of intermolecular forces. And lastly, what is the impact in molecular properties such as boiling point and solubility, things that we use a lot in organic chemistry. So you will find always questions on exams about ranking compounds according to increasing or decreasing boiling point or solubility and things like that. So that's why we need to understand that. Plus, at the lab, this is very useful to be able to predict where the two substances are admissible, something is soluble in something else. And this is why this topic is important for us in organic chemistry. Again, it's reviewing something from your chem. So let's get to a few molecules that I'm sure that you guys saw in your Gen Chem. So let's talk about water, for example. So oxygen, we know where that is in the periodic table, but let's remind us. Second period is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and here's neon. Noble gases are here. Right here is chlorine, and we have a lot of halides in organic compounds. Here, right under oxygen, we have sulfur. Right under nitrogen, we have phosphorus. So those are common elements in organic molecules. Of course, hydrogen, because hydrocarbons essentially will have carbon and hydrogen. Now we have other functional groups, and so we will have other atoms, which we call heteroatoms. Now, this is water. In now group 1, 2, 3, 4, I'm going to write a number 4 here, 5, 6. That means that's the number of valence electrons. So 6 valence electrons in oxygen and so forth. So this is what we get. So I'm going to say that I'm going to just illustrate first just the Lewis dot structure. And so I'm going to say oxygen has 6 valence electrons, 1, 2, 3, and 4. And here is making one sigma bond by sharing one electron from the hydrogen, essentially. And now we translate that the Lewis structure, you can draw it straight like that. But now the other concept, molecular geometry, here, what we need to be reviewing is VSEPR theory, valence shell electron pair repulsion. So quickly here, let's talk about electron domains. 1, 2, 3, and 4 electron domains. For that theory, we place those electron domains as separate as possible. Because we have 4, we're going to start doing that in putting those electrons in the direction of a tetrahedral structure. So I'm going to put oxygen here, and I'm going to say that I'm going to put the 4, say, corners of a tetrahedron. And same, these are 4 domains. If I had methane, which is CH4, the Lewis structure is 4 bonds. We know how to do that. 4 valence electrons of the carbon and 1 from each of the hydrogen makes these 4 sigma bond. So let's do methane here. So again, 4, 1, 2, 3, 4 electron domains. So we're going to put those in a tetrahedral structure. Now here the 4 domains, the 4 electron domains are actually bonding. These are bonds. So now we're going to complete the structure of methane by adding the H's. So 4 hydrogen. The geometry of this molecule, again, you're placing those in the tetrahedral structure so that they are as separated as possible according to this theory. So in here, the tetrahedral structure, the angles are going to be 109.5. And so the geometry is tetrahedral. Again, we're using this theory to predict molecular geometry. Now, the other factor that we said that impacts if the molecule is polar or not, and therefore impacts the way molecules interact, the molecular forces, then the other factor is whether we have polar bonds or not. In organic chemistry, we make a definition here, the bond between carbon and hydrogen. There is a small difference in electronegativity, but this is in Pauli's scale, 0.4. So we're going to say this is simply polar covalent. I'm sorry, not polar, non-polar, simply a covalent bond. So that's my threshold. So any difference in electronegativity that is smaller or equal to 0.4, we're going to classify that as covalent bond simply. So it's not polar. And if it is greater than 0.4, then we're going to say is polar covalent. Now, there is another threshold. If that difference is about 1.7, we're going to say is ionic. But most cases, this is what we're going to be dealing. So what's the difference? I know my trends in electronegativity go this way. So increasing from left to right. So here the most electronegative atom in this period and in the whole periodic table is fluorine. It's refusing to do that line. Okay. Now electronegativity also increases from the bottom up. So overall the trend is like a diagonal line. So fluorine is the most electronegative. So here again, there is a difference between hydrogen and carbon, but it's small. So we're going to consider that simply covalent. Other than that, a bond between carbon and hydrogen will be polar. Between carbon and oxygen will be polar. Carbon and fluorine, carbon and chlorine, and so on. Now, because these are non-polar bonds, according to our definition, we don't draw any arrows. Polar bonds, we're going to illustrate those bonds by drawing an arrow. That arrow is another way of saying that there is a part of the molecule that will be lacking some electron density, and we'll say this is delta positive, in another portion that will be delta negative. That's that. So that is how I illustrate that my bond is polar. In methane, I don't have that, but in water, I have polar bonds. And now let's place the electrons here. I have, this is my Lewis structure. So I'm going to put electrons here. So one of the domains, another domain will have electrons. And now I have a couple of hydrogens. Notice that the geometry is not linear as it is drawn here in the Lewis structure. This geometry, there is an angle here, about 108. And this geometry we say is bent. So because of that, now, and because one thing, again, the geometry and the nature of the bonds. These bonds are polar, and they are polarized towards the oxygen. Because, again, you start the arrow at the delta positive, so the least electronegative atom, and you end the arrow at the more, say, delta negative, at the more electronegative. This is why the arrows are pointing that way, but I'm going to translate these two arrows to a common origin, so I'm going to copy that here, roughly. And now I'm going to translate the other arrow. So if you do this, so what are we doing? We're adding those two vectors. So if I do that, then I'm going to do the sum of the vectors. So it's not zero. They do not cancel out. So the molecule has a dipole moment. So again, just reviewing, determining your Lewis structure, then determine the molecular geometry, determine whether you have polar bonds or not, and then depending on the geometry and the polar bonds, you will determine if the molecule is polar or not. So water is polar and methane is not. We're going to continue that in another video.